Hello there, and welcome to Sleepy Science. Most people imagine the Big Bang as a huge explosion in space. The truth is stranger. It didn't happen in space. Space itself came into existence at that moment. There was no center, no edge, and nothing outside it. Everything, every galaxy, every atom, every corner of the universe began expanding all at once. Even stranger, the earliest light from that moment is still traveling through the universe today, carrying tiny variations that eventually became the galaxies, stars, and planets you see. By the end of this video, you'll understand not just how the universe began, but why its beginning was both extreme and calm at the same time. Most people think the Big Bang was like a single explosion, a blast from one point sending matter outward. That is not correct. The Big Bang happened everywhere at the same time. Every part of space started expanding simultaneously. There wasn't one location that burst. The entire universe, all points in space, began growing together. Imagine the universe as a balloon. Instead of a dot popping, the balloon itself is stretching. Every part moves away from every other part equally. This means that no matter where you are, the Big Bang was happening around you, not somewhere far away. The strange and fascinating part is that the universe's expansion started from a state where space, time, and matter were all combined, not separated. That's why the Big Bang is not a simple explosion. It's the creation of space itself, happening everywhere at once in the calmest way you can imagine. There is no center of the Big Bang. Unlike explosions you see in movies, there wasn't a single location where the universe started, and there isn't a central point in space today. Every observer from any galaxy sees the universe expanding around them. This happens because space itself is stretching, and everything embedded in it moves with it. There isn't a middle to point at because space didn't exist before the Big Bang. Even light from the earliest universe doesn't come from a single spot. It comes from every direction. This challenges our everyday idea of a center. The universe has no edge and no outside. Thinking of it as a growing grid helps. The grid itself expands, and everything on it moves apart, but no part is more central than another. The Big Bang created a uniform space that has no special place, yet from every vantage point, it looks like the universe is spreading out. Every observer in the universe sees galaxies moving away from them, and that can feel surprising. If the universe is expanding everywhere at once, why do all points seem to be moving outward from each observer? This is because space itself stretches uniformly, so every galaxy appears to recede from every other galaxy. Imagine dots on the surface of a balloon being inflated. If you stand on one dot, every other dot seems to move away, even though all dots move in the same way. This is exactly what astronomers observe when they measure galaxy speeds. The farther a galaxy is, the faster it appears to move away. This observation is consistent across the sky, which supports the idea that the universe is expanding evenly. The fascinating part is that there is no preferred observer. Every vantage point shows the same expansion. That's why the universe doesn't need a center, and expansion feels universal to everyone. Space itself expands. It is not that objects are moving through space. This is one of the hardest ideas to grasp. Imagine stretching a rubber sheet with small beads on it. The beads don't move on the sheet. They move apart because the sheet itself stretches. In the same way, galaxies aren't flying through space. The space between them is increasing. This expansion happens everywhere all the time, and it even stretches light waves, making distant galaxies appear redder. The key point is that the fabric of space is dynamic, not fixed. Even empty space contributes to this expansion. Nothing pushes the galaxies. They just separate as the universe grows. This is why distant galaxies appear faster than closer ones. The idea is strange, but it is what explains why the universe looks uniform and why cosmic observations match predictions from the Big Bang. Space is not static. It is alive with slow, constant expansion. In the earliest moments of the universe, space expanded faster than the speed of light. This seems impossible at first, because nothing can move faster than light, right? The key is that it wasn't objects moving through space, it was space itself stretching. During a fraction of a second, the universe grew from a size smaller than an atom to something much larger than a galaxy. This incredible growth happened almost instantly, and it created the smooth and even universe we see today. The strange part is that this means distant regions of space were pushed far apart in less time than light could travel between them. Without this extremely fast expansion, distant areas of the universe would never have been able to share information, and the cosmos would look very different. This rapid stretching is called inflation, and it set the stage for everything that followed, giving the universe its large-scale uniformity. Even though space expanded faster than light, it does not break Einstein's theory of relativity. Relativity limits objects moving through space, but space itself is not an object. It can grow without limit. The speed limit only applies to matter and information traveling inside space, not the expansion of space itself. Imagine drawing dots on a stretchy rubber sheet and quickly stretching it. The dots aren't moving on the sheet, but the distance between them increases. That is exactly what happened in the early universe. Relativity remains valid, but it only governs motion within space, not the creation or stretching of space itself. This is why scientists can say parts of the universe moved apart faster than light without breaking physics. It is one of the most unusual and fascinating facts about the Big Bang, because it shows how the rules of space and motion behave differently at the largest scales, in ways that challenge our everyday intuition. This period of rapid expansion, called inflation, lasted less than a second. It is almost impossible to imagine such a short amount of time, yet during that tiny fraction, the universe grew unimaginably. The duration of inflation is so brief that it cannot be measured with ordinary clocks. It is only understood through the effects it left behind. Tiny differences in temperature and density that existed before inflation were stretched into patterns that later guided the formation of galaxies. The speed and brevity of this event are what make it both mysterious and essential. Without this short period, the universe would not have achieved the smoothness we see on a cosmic scale. The entire large-scale structure of the universe, including clusters of galaxies and the distribution of matter, depends on what happened in this invisible, almost instantaneous moment. Understanding inflation helps explain why the universe looks organized, even though its beginning was extreme. Inflation increased the universe's size by an unimaginable factor. In less than a second, the universe expanded by a number so huge that it is almost impossible to describe. Regions that were once microscopic became larger than entire galaxies. This explains why the universe appears so uniform when we look in any direction. Areas that now seem far apart were once close enough to share energy and information. Inflation also smoothed out irregularities, but it preserved tiny differences that became the seeds for galaxies and stars. The expansion stretched space itself, carrying all matter and energy along. It is a quiet process, not violent like an explosion, but its consequences are enormous. The universe went from almost nothing to an enormous space filled with potential, setting the stage for stars, planets, and eventually life. This rapid growth is one of the strangest and most important facts about the Big Bang, showing that the universe's earliest moments were both brief and unimaginably vast. Without inflation, galaxies would not exist. Before inflation, The universe was incredibly small and uneven at the tiniest scales. Any small irregularity could have prevented matter from clumping together. Inflation stretched these tiny regions, making them smooth but leaving small variations in density. These slight differences were essential because they acted as seeds for matter to gather under gravity. Without inflation, the universe would have been too chaotic for stars and galaxies to form, and large-scale structures like clusters and superclusters would never have appeared. In other words, the quiet, rapid stretching of space allowed order to emerge from the very beginning. Everything we see in the night sky, from the Milky Way to distant galaxies billions of light years away, exists because of this brief, invisible moment. It is strange to think that the formation of galaxies depended on something so fast and almost unnoticeable, yet it shaped the universe forever. Inflation left permanent imprints on the universe, which is one of the strangest aspects of this event. Even though the expansion happened extremely fast and ended billions of years ago, it left tiny variations in energy and density. These imprints acted like a cosmic blueprint. They were small enough to be almost invisible, but large enough to guide the formation of stars, galaxies, and clusters. In essence, inflation not only stretched space but also wrote information into the universe itself. Scientists call these imprints quantum fluctuations that became the seeds for all structure. What is fascinating is that these marks are still present today, even though the universe has grown and changed unimaginably. They are a permanent record of an event that lasted less than a second, showing that the earliest moments of the universe shaped everything that followed, and left clues that we can still detect billions of years later. These imprints are still visible in the cosmic microwave background radiation, the oldest light in the universe. About 380,000 years after the Big Bang, the universe cooled enough for light to travel freely. That light carries a snapshot of the density variations left by inflation. Today, scientists can detect tiny differences in temperature across the sky in this radiation. These differences are incredibly small, only a few millionths of a degree, but they correspond directly to the imprints of inflation. By studying them, astronomers can map where matter was slightly denser or lighter in the early universe. These areas later became galaxies, clusters, and voids. It's remarkable to think that we can observe the universe's first moments in this way. The cosmic microwave background is like a faint echo of the Big Bang, still present everywhere, quietly telling the story of how the universe began and how every galaxy came to be. Satellites can measure these tiny temperature differences with extraordinary precision. Instruments like the Planck and WMAP satellites scan the sky to detect minute variations in the cosmic microwave background radiation. They measure differences as small as a few millionths of a degree Celsius, which allows scientists to map the earliest structure of the universe. These temperature maps show the spots where matter was slightly denser or less dense, revealing the blueprint left by inflation. By analyzing these patterns, scientists can test theories about the early universe, including how fast it expanded, how uniform it became, and how the first galaxies formed. It is amazing to think that human technology can detect such tiny traces from nearly 14 billion years ago. This ability to measure the faintest signals proves that even the smallest events in the earliest universe had enormous consequences, shaping everything we see today. The temperature differences seen in the cosmic background radiation are extremely small, only a few millionths of a degree. This number is so tiny that it is hard to imagine, yet it carries huge meaning. These slight changes show where the early universe was a little warmer or cooler. Warmer areas had slightly more energy and matter, while cooler areas had slightly less. At the time, these differences did not seem important, but they quietly shaped everything that came later. What makes this strange is how evenly balanced the universe was. Across the entire sky, the temperature is almost the same, showing that the early universe was remarkably smooth. The fact that scientists can measure such tiny differences at all is surprising. These nearly perfect conditions explain why the universe looks similar in every direction, while still allowing enough variation for structure to form. Those tiny temperature differences later formed galaxy clusters. Over millions of years, gravity began pulling matter toward the slightly denser regions seen in the early universe. Areas with just a little more matter attracted even more matter over time. This slow process allowed stars, galaxies, and eventually large clusters of galaxies to form. The fascinating part is that massive galaxy clusters began as differences so small they could barely be measured. Without those early variations, matter would have remained evenly spread, and nothing large would have formed. The universe would be filled with gas, but no stars or galaxies. Instead, gravity amplified those small differences, turning them into vast cosmic structures. This explains why galaxies are grouped together instead of evenly spread across space. The universe did not start with big structures. It grew them slowly from tiny beginnings that inflation preserved. Quantum randomness played a key role in shaping the universe. At the smallest scales, the universe does not behave in a smooth or predictable way. Instead, energy appears and disappears randomly due to quantum effects. During inflation, these tiny random changes were stretched across enormous distances. What started as small, random fluctuations became the seeds for all structure. This means the large-scale universe we see today is partly the result of randomness at the smallest level. This idea feels unsettling at first, because it suggests the universe is not perfectly planned or uniform. Instead, it developed patterns from chance events. Yet these random effects followed physical laws, allowing order to emerge. Without quantum randomness, the universe would be too smooth, and galaxies would never have formed. Randomness, in this case, made structure possible. Randomness at microscopic scales affects the largest structures in the universe in surprising ways. The tiny quantum fluctuations that existed at the beginning were stretched by inflation to sizes larger than galaxies. Over time, gravity took these stretched patterns and turned them into real structures. This means the placement of galaxies and clusters can be traced back to random events in the early universe. It is strange to think that something smaller than an atom influenced structures millions of light-years wide. This connection between the smallest and largest scales shows how deeply connected the universe is. Small events did not disappear. They were preserved and amplified. This is why scientists say the universe remembers its earliest moments. Even today, the largest structures in space carry the imprint of tiny, random changes that happened at the very beginning. In the earliest moments after the Big Bang, the universe behaved more like pure energy than matter. Temperatures were so high that stable matter could not exist yet. Instead of solid particles, the universe was filled with intense energy moving everywhere. Energy and matter were not clearly separate at this stage. According to physics, energy can turn into matter and matter can turn back into energy, and this was happening constantly. The universe was too hot and dense for anything solid or long-lasting to form. This is very different from the universe today, where matter stays mostly stable. Back then, energy ruled everything. As the universe expanded and cooled, energy slowly transformed into matter. This change allowed particles to begin forming and lasting longer. Understanding this stage helps explain why matter exists at all. Without this cooling process, the universe would never have moved beyond a state of pure energy. At this early stage, particles did not have stable identities. Today, we think of particles like electrons and quarks as having fixed properties. But in the early universe, conditions were too extreme for that. Particles constantly changed their behavior, and some types could not exist yet. Forces that are separate today, like electromagnetism and nuclear forces, were once combined. Because of this, particles did not act the way they do now. Their masses were not fixed, and their interactions were unpredictable. This meant the universe had no permanent building blocks yet. Everything was temporary and flexible. Only after the universe cooled did particles settle into stable forms with clear identities. This moment was critical, because stable particles allowed atoms to eventually form. Without this stage, the universe would have remained a shifting sea of energy with no lasting structure. Particles in the early universe constantly appeared and disappeared. Energy was so intense that it regularly turned into pairs of particles and antiparticles. These pairs would form briefly and then destroy each other, turning back into energy. This process happened everywhere all the time. Nothing stayed for long. A particle could exist for a tiny moment and then vanish. This sounds chaotic, but it followed clear physical rules. The universe was balanced between creation and destruction. As long as temperatures stayed high, particles could not remain stable. This constant appearing and disappearing shows how active the early universe was, even though it had no stars or galaxies yet. Only when the universe cooled enough did some particles stop disappearing and begin to survive. That moment changed everything, allowing matter to slowly take over. Nothing could exist for long in the early universe because the conditions were too extreme. The intense heat and pressure prevented stability. Any structure that tried to form was quickly broken apart by energy. Atoms could not exist, particles could not stay together, and even forces behaved differently. The universe was expanding rapidly, but it was still far too hot to allow anything permanent. This phase did not last long, but it was essential. As expansion continued, temperatures dropped and stability slowly became possible. This cooling allowed particles to stop vanishing and begin forming lasting matter. Only then could the universe move toward creating atoms, stars, and galaxies. The strange part is that existence itself required the universe to calm down. Stability was not the starting point. It was something the universe slowly earned as it expanded. In the early universe, matter almost completely destroyed itself. When particles formed, they were usually created in pairs. One particle of matter and one of antimatter. When matter and antimatter meet, they instantly destroy each other and turn back into energy. This happened constantly in the hot early universe. Every time a particle appeared, its opposite appeared too. They collided and vanished again and again. Because of this, it seems like matter should not exist today at all. The universe could have ended up as pure energy with no atoms, stars, or planets. This near-total destruction is one of the strangest facts about the Big Bang. The universe produced matter, then almost erased it completely. Understanding why matter survived at all is one of the biggest questions in physics, because without survival, there would be nothing left to form the universe we know. Antimatter was nearly equal to matter in the early universe. For every particle of matter, there was almost exactly one particle of antimatter. They had the same mass but opposite properties, such as electric charge. Because they were produced together, the universe began in near-perfect balance. This balance meant that destruction was almost total. When matter and antimatter met, they turned into energy without leaving anything behind. Scientists believe the difference between matter and antimatter was incredibly small. The universe was not designed to favor matter strongly. Instead, it was nearly neutral. This makes the existence of galaxies and life feel even more surprising. If the balance had been perfect, all matter would have disappeared. The fact that antimatter was so close in number to matter shows how delicate the early universe was, balanced on a knife edge between existence and nothing. A tiny imbalance allowed matter to survive. For reasons scientists are still trying to fully understand, there was a slight excess of matter compared to antimatter. This imbalance was extremely small, but it was enough. When matter and antimatter destroyed each other, most of both vanished. However, that small extra amount of matter had nothing to cancel it out. It remained after the universe cooled. This leftover matter became the building material for everything that exists today. Without this imbalance, the universe would be empty. What makes this fascinating is how small the difference was. The universe did not need a large advantage for matter, only a tiny one. This shows how sensitive the universe was to its starting conditions. A very small difference at the beginning led to a universe filled with stars, planets, and life billions of years later. One extra particle per billion changed everything. For every billion pairs of matter and antimatter particles, there was about one extra particle of matter. That single leftover particle survived after all the others destroyed each other. Over time, these tiny leftovers added up. They formed atoms, then stars, then galaxies. This number is so small that it is hard to believe it could have such a huge effect. Yet without it, there would be no solid matter anywhere. Every object you see is made from those leftover particles. This fact shows how the universe depends on extremely small differences. A tiny imbalance in the early universe determined whether anything would exist at all. The universe did not need a large change, just one extra particle per billion, to go from near nothingness to everything we observe today. Without the small imbalance between matter and antimatter, no atoms would exist. If matter and antimatter had been created in exactly equal amounts, they would have destroyed each other completely. Nothing solid would have remained. No protons, no electrons, and no atoms. The universe would be filled only with energy spreading thinner as space expanded. Atoms are the basic units of everything we see, and they require stable matter to exist. That small leftover amount of matter allowed particles to join and form structure. It is surprising that the entire universe depends on such a tiny difference. Every atom in your body exists because matter was not perfectly balanced at the beginning. This shows how sensitive the universe was in its earliest moments. A small change decided whether there would be a universe full of matter or one completely empty of structure. One strange fact is that physics does not fully explain why this imbalance happened. Scientists know that matter slightly outnumbered antimatter, but they do not yet know exactly why. Current theories explain part of the process, but not all of it. This gap in understanding is important because it shows that our knowledge of the universe is still incomplete. The laws of physics describe how particles behave, but they do not clearly explain why the universe favored matter just enough. This mystery is one reason scientists continue to study the early universe. The fact that such a crucial event is not fully understood makes the Big Bang even more interesting. It reminds us that the universe still holds unanswered questions, even about the events that made existence possible. Protons formed before atoms. After the universe cooled enough for particles to survive, quarks joined together to form protons and neutrons. These particles became the cores of future atoms. At this stage, the universe was still extremely hot, but stable particles could finally exist. Protons are positively charged and would later attract electrons to form atoms. However, at this early time, protons existed alone, without electrons attached. This phase lasted for hundreds of thousands of years. The universe had the ingredients for atoms, but it was not yet ready to assemble them. This shows that atom formation was not immediate. It happened in steps, as conditions slowly changed. Understanding this process helps explain why the universe developed gradually rather than all at once. Electrons could not attach to protons immediately because the universe was still too hot. High temperatures meant electrons moved too fast to stay attached. Whenever an electron tried to join a proton, energy from heat would knock it away. This prevented atoms from forming. Instead, the universe remained a hot plasma of free particles. Light also could not travel freely during this time because it constantly interacted with charged particles. Only after the universe expanded and cooled further did electrons slow down enough to attach to protons. When that finally happened, atoms formed and light was released. This moment changed the universe completely. It allowed space to become transparent and marked the beginning of a universe where structures could grow. Stability required patience, and the universe had to cool before anything lasting could form. Light was trapped for hundreds of thousands of years after the Big Bang. During this time, the universe was filled with charged particles like free electrons and protons. Light could not travel far without hitting one of these particles and scattering. Every photon was constantly blocked, bounced, or absorbed. This meant the universe was not transparent. Even though light existed, it could not move freely through space. The universe was bright, but nothing could be seen through it. This trapped light phase lasted about 380,000 years, which is very long compared to the earlier moments of the universe. It may seem strange that light existed but could not travel, yet this is exactly what happened. Only when conditions changed did light finally escape, allowing the universe to reveal itself for the first time. During this trapped light phase, the universe was like a hot, glowing fog. It was filled with energy, particles, and radiation all mixed together. The temperature was still extremely high, so particles moved rapidly and collided constantly. This made the universe opaque, similar to how fog blocks visibility on Earth. Light was everywhere, but it could not move far before being scattered. There were no stars or galaxies yet, just a uniform glow. This fog filled all of space, leaving no clear view in any direction. The universe was smooth and evenly lit, but also hidden. This stage shows that brightness does not always mean visibility. Even though the universe was glowing intensely, nothing could be seen through it. Everything remained concealed until the universe cooled enough for change. The fog suddenly cleared when the universe cooled to a critical temperature. As space expanded, temperatures dropped and particles slowed down. At a certain point, electrons finally moved slowly enough to attach to protons. When this happened, charged particles became neutral atoms. This change happened across the entire universe. Once electrons were no longer free, they stopped scattering light. In a relatively short time, the universe changed from opaque to transparent. This transition was not gradual. It happened quickly once the right conditions were reached. The universe went from being completely foggy to clear. This moment is one of the most important transitions in cosmic history. It allowed light to move freely for the first time and marked the beginning of a visible universe. This moment released free light because neutral atoms do not block photons the way charged particles do. Once electrons attached to protons, light no longer collided constantly with matter. Photons were able to travel long distances without interruption. The light that was released at this time is still traveling through space today. It has cooled and stretched as the universe expanded, but it still exists. This released light became the cosmic background radiation we can detect now. It is a direct signal from the early universe. This event marks the first time the universe became transparent. From that point on, light could carry information across space. The release of free light allowed the universe to develop structure and gave us a way to observe its earliest history. The light released when the universe became transparent still exists today. After electrons attached to protons and light was freed, those photons began traveling through space. Nothing stopped them. As the universe expanded, the light kept moving, filling all of space. Even though billions of years have passed, that light was never destroyed. It simply continued its journey while space around it stretched. This means the universe still carries a visible record of its early state. Scientists can detect this ancient light using sensitive instruments. It is not coming from stars or galaxies. It comes from the universe itself. This is surprising because it means we are surrounded by light that is almost as old as time. Every direction you look contains this ancient signal, quietly present and unchanged in origin, even though the universe has grown enormously since then. As the universe expanded, this light cooled and shifted to microwave frequencies. When space stretches, it also stretches the waves of light traveling through it. Early light was extremely hot and energetic, but expansion caused its wavelength to grow longer. Longer wavelengths mean lower energy and lower temperature. Over billions of years, this light cooled from a bright glow to faint microwave radiation. Today, its temperature is just a few degrees above absolute zero. This cooling process did not require anything to absorb the light. It happened naturally because space itself expanded. This shows how expansion affects everything, even radiation. What began as visible light is now invisible to human eyes but still measurable. The change in frequency is a direct record of how much the universe has grown. By measuring this radiation, scientists can calculate the universe's age and expansion history. This radiation comes from all directions because it was released everywhere at the same time. When the universe became transparent, every region of space released light simultaneously. Since there was no center to the universe, the light did not come from one location. As the universe expanded, that light spread out uniformly. No matter where an observer is located, they see the same background radiation in every direction. This uniformity tells scientists that the early universe was nearly the same everywhere. It also supports the idea that the Big Bang happened everywhere at once. The radiation is not coming toward us from a distant place. It already surrounds us. We are inside it. This makes the cosmic background radiation unique. It is not distant in space, but distant in time, giving us a view of the universe's earliest visible moment. This radiation is the oldest thing we can observe. It formed long before any stars, galaxies, or planets existed. Everything else we see in space formed later. Even the most distant galaxies are younger than this radiation. Because light travels at a finite speed, observing distant objects means looking back in time. The cosmic background radiation takes this idea to the extreme. It shows the universe as it was shortly after atoms first formed. There is nothing observable from earlier times because light could not travel freely before this moment. This makes the radiation a hard limit on how far back we can see. It is the earliest image the universe allows us to observe. Through it, scientists study the conditions that shaped everything that followed, making it one of the most valuable sources of information about the universe's beginning. This ancient radiation predates all stars and galaxies. It was released long before the first star ever ignited. At the time this light began traveling freely, the universe was still dark and empty of visible objects. There were no galaxies, no planets, and no heavy elements. The radiation comes from a time when the universe was simple and uniform. Stars and galaxies formed hundreds of millions of years later, after gravity slowly pulled matter together. This means when scientists observe this radiation, they are looking at the universe before any structure existed. It is a snapshot of the universe in its earliest visible state. Everything that came later, including stars and galaxies, formed on top of the conditions seen in this radiation. That makes it a reference point for understanding how complexity grew from simplicity. One strange fact is that space itself has a measurable temperature. Even in the emptiest regions of the universe, where there are no stars or galaxies, space is not at absolute zero. The temperature comes from the leftover radiation from the early universe. This background radiation fills all of space and gives it a measurable warmth. Scientists can measure this temperature very precisely using sensitive instruments. It is only a few degrees above absolute zero, but it is present everywhere. This means empty space is not truly empty. It carries energy from the universe's beginning. The idea that space has a temperature challenges the common belief that space is completely cold and lifeless. Instead, it shows that the universe still holds traces of its early heat, spread evenly across all of space. Even empty space is not truly cold because it is filled with low-energy radiation. This radiation is the leftover light from the early universe, stretched and cooled over time. Although it is very faint, it still adds energy to space. This is why scientists say space has a background temperature. Absolute zero is a theoretical limit that space never fully reaches. Even far from stars, this radiation remains. It provides a constant temperature floor for the universe. This fact shows that the universe is never completely silent or inactive. Even in its emptiest regions, it carries a faint echo of its beginning. This background energy affects how matter behaves at very low temperatures and plays a role in cosmic measurements. The universe always remembers its past, even in places that seem completely empty. Expansion cools radiation by stretching its wavelength. As space expands, the waves of light traveling through it become longer. Longer wavelengths mean lower energy and lower temperature. This process happens slowly but continuously. The radiation released early in the universe started out hot and energetic. Over billions of years, expansion stretched it into the faint microwave radiation we detect today. This cooling does not require radiation to lose energy through collisions. It happens simply because space itself is growing. This is one of the clearest examples of how expansion affects the universe. By measuring how much this radiation has cooled, scientists can calculate how much the universe has expanded. The cooling of radiation is a direct record of cosmic growth, quietly tracking the universe's long history. The universe never stopped expanding because the Big Bang did not push matter outward and then fade away. Instead, it created space itself in an expanding state. Once expansion began, there was no reason for it to suddenly stop. The universe had no outer wall to hit and no surrounding space to slow it down. Expansion became part of how space behaves. Even after the early rapid expansion ended, space kept stretching. Matter and energy moved within this expanding space, but the expansion itself continued quietly in the background. This is important because it explains why the universe is still growing today, billions of years later. Expansion was not a one-time event. It became a long-term process. The strange part is that nothing needs to push the universe anymore. Space expands simply because that is how it was set in motion at the beginning, and once started, it kept going. Expansion does not slow uniformly across the universe. At first, scientists expected expansion to gradually slow down at a steady rate because of gravity, but observations showed something unexpected. Some regions appear to expand differently over time. Early in the universe, expansion slowed more noticeably as matter pulled on itself. Later, expansion behavior changed. This tells scientists that expansion is not controlled by a single simple factor. It depends on how much matter and energy exist and how they interact with space. This uneven slowing made scientists realize that expansion history has different phases. The universe expanded rapidly at first, then slowed, and later behaved differently again. This changing behavior is one of the clues that something else is influencing expansion. It shows that the universe's growth is not a simple straight line, but a complex process that changes as conditions evolve. Gravity tried to slow the expansion of the universe by pulling matter together. Gravity is an attractive force, and as matter formed, it began pulling inward. Galaxies attracted other galaxies, and large structures formed. This inward pull worked against expansion. In the early universe, gravity did slow expansion more strongly because matter was closer together. Scientists once believed gravity might eventually stop expansion entirely. If enough matter existed, the universe could slow, stop, and possibly collapse. This idea made sense based on what gravity does locally. However, as the universe expanded, matter became more spread out. Gravity's influence weakened over large distances. Although gravity still shapes galaxies and clusters, it could not fully stop the overall expansion of space. This created a balance between inward pull and outward stretching that lasted for billions of years. Dark energy is the effect that counteracts gravity and changes expansion behavior. Scientists discovered it when they observed distant supernovae appearing dimmer than expected. This showed that expansion was not slowing as predicted. Instead, it was speeding up. Dark energy is not a substance like matter. It is a property of space itself that causes space to expand faster as it grows. The more space there is, the stronger this effect becomes. This idea was surprising because it means empty space has energy. Dark energy does not pull things together. It pushes space apart. It does not affect small objects like planets, but it dominates the universe at large scales. This discovery changed how scientists understand the universe's future and revealed that expansion is driven by more than just matter and gravity. Dark energy was completely unknown until the late 1990s. Before that time, scientists believed the universe's expansion should be slowing down because of gravity. Most theories focused only on matter, radiation, and gravity. There was no need for another force, and no clear evidence for one. That changed when new telescopes and better tools allowed scientists to study very distant objects in detail. When researchers compared old predictions with real data, they noticed something did not match. The universe was not behaving as expected. This discovery was surprising because it challenged long-held ideas. Dark energy was not predicted clearly by earlier models. It was introduced only because observations demanded an explanation. This makes dark energy unusual in science. It was not found by theory first, but by evidence forcing scientists to rethink how the universe works. Supernova observations revealed dark energy in an unexpected way. Scientists studied a special type of exploding star called a Type Ia supernova. These explosions shine with nearly the same brightness every time. Because of this, they act like distance markers. By comparing how bright they appear from Earth to how bright they should be, scientists can calculate how far away they are. In the late 1990s, teams observed very distant supernovae and found them fainter than expected. This meant they were farther away than predicted. The only explanation was that the universe expanded more than expected while the light was traveling. This discovery came from careful measurement, not guesswork. When many supernovae showed the same result, scientists realized something new was affecting expansion. That effect was later named dark energy. Distant galaxies appear dimmer than expected because space has expanded more than predicted during the light's journey. Light from far galaxies travels for billions of years before reaching Earth. While it travels, space itself stretches. This stretching spreads the light out, making it weaker when it arrives. Scientists originally thought expansion slowed down, so they expected a certain brightness level. But observations showed the galaxies were dimmer, meaning they were farther away. This extra distance could not be explained by gravity alone. The dimness was not caused by dust or faulty tools because the pattern appeared consistently. The farther the galaxy, the larger the effect. This told scientists that expansion did not slow over time as expected. Instead, something caused space to stretch more than planned models allowed. That clue pointed directly toward a new force affecting the universe. Expansion began accelerating when dark energy started to dominate over gravity. In the early universe, matter was packed closely together and gravity had a stronger influence. Expansion slowed during that time. As the universe grew, matter spread out and gravity weakened over large distances. Dark energy, however, did not weaken. Because it is linked to space itself, it became more powerful as space increased. At a certain point, dark energy's effect became stronger than gravity's pull. When that happened, expansion stopped slowing and began speeding up. This change did not happen suddenly but gradually. Once acceleration started, it continued and still continues today. This explains why distant galaxies move away faster now than they did in the past, changing our understanding of the universe's future. The acceleration of the universe increases over time because dark energy becomes more important as space grows. In the early universe, matter was close together, and gravity had a strong pull that slowed expansion. As the universe expanded, matter spread out and gravity weakened over large distances. Dark energy works differently. It is not tied to matter or objects. It is linked to space itself. As space increases, dark energy does not fade. This creates a strange situation where the force pushing the universe apart slowly becomes stronger than the force pulling it together. Over billions of years, this balance changed. Gravity lost its grip and expansion began to speed up. The more the universe expands, the less gravity can slow it down. This creates a feedback effect. Expansion makes dark energy dominate more, which causes even faster expansion. That is why acceleration is not stopping. One strange fact is that empty space itself appears to create energy. Dark energy is not found inside stars, planets, or galaxies. It exists even where there is nothing at all. If you remove all matter from a region of space, dark energy is still there. This is surprising because empty space was once thought to be truly empty. Scientists now believe space has its own energy built into it. This energy does not come from particles or heat. It comes from space simply existing. The larger the space, the more of this energy exists. This idea feels strange because energy is usually linked to objects or motion. Here, nothingness plays a role. This discovery changed how scientists think about the universe. It suggests that space is active, not passive. Even regions with no stars or gas still affect how the universe grows. Dark energy density stays constant even as the universe expands. Density means how much energy exists in a certain amount of space. For matter, density drops as space grows because the same matter spreads out. Dark energy does not behave this way. If you measure 1 cubic meter of space today or billions of years ago, it contains the same amount of dark energy. This is very unusual. Most things dilute when space expands, but dark energy does not. This constant density is key to understanding why expansion accelerates. As the universe grows, more space appears, and each new part contains dark energy. Gravity weakens, but dark energy keeps the same strength everywhere. This makes it more powerful over time compared to matter. Scientists still do not fully understand why dark energy stays constant. They only know that observations strongly support this behavior. Expansion creates more dark energy overall because new space keeps forming. Even though the density stays the same, the total amount increases as space grows. Imagine space like a growing grid. Each new section added contains dark energy. As the universe expands, the number of these sections increases. This means the total dark energy increases too. This does not break known rules because the energy is part of space itself. When space expands, the energy comes with it. This helps explain why acceleration continues and even strengthens. More space means more dark energy pushing outward. Matter does not increase the same way, so it becomes less important over time. This process makes the universe behave very differently than scientists once expected. It also raises deep questions about where this energy truly comes from and what it means for the future of the universe. This leads to increasing acceleration because dark energy becomes more dominant as the universe grows. Since dark energy's density stays constant, the more space there is, the more total dark energy exists. Gravity, which tries to slow expansion, weakens as matter spreads out over greater distances. With dark energy pushing outward everywhere and gravity becoming less effective, expansion accelerates faster over time. This is different from what scientists once expected, when they thought expansion would slow or even stop. The acceleration is self-reinforcing. As the universe expands, there is more space, so there is more dark energy, which pushes space apart even faster. Over billions of years, this effect will continue to grow. The strange part is that the universe does not need a force in the usual sense. Expansion speeds up simply because dark energy dominates over gravity across all of space, and there is no limit to how much space can expand. Eventually, galaxies will disappear from view for future observers. As expansion accelerates, galaxies that are not gravitationally bound to us will move away faster and faster. Over extremely long timescales, the light from these galaxies will no longer reach Earth or any other point in our region of the universe. From that vantage point, the night sky would appear nearly empty, filled only with local galaxies that remain gravitationally connected. Distant stars and galaxies will fade and vanish beyond the observable horizon. This means the universe will look much smaller and darker than it does today. It is remarkable to think that billions of years from now, intelligent observers could live in a universe that appears almost completely isolated, without any evidence of the vast structures we see now. The cosmic landscape will be dominated only by a few local galaxies. Future observers will not see evidence of the Big Bang the way we do today. With galaxies disappearing beyond the observable horizon, there will be no distant objects to study that formed from the early universe. Without supernovae and distant galaxies to measure, it will be nearly impossible for future scientists to detect the expansion of space. The cosmic microwave background radiation will also fade and stretch beyond detectable wavelengths. This means the clues we currently have about the universe's origin, its age, structure, and history, will vanish from view. It is strange to realize that the universe we observe today is unique in its accessibility. Observers far in the future will see only a limited local universe. The full story of the Big Bang will become invisible, leaving them with no way to understand the universe's early moments or how it all began. Cosmic background radiation will fade as space continues expanding. Its wavelength will stretch longer and longer over time, moving beyond the microwave range into even lower energy waves. Eventually, it will become so faint and low in energy that no instruments will be able to detect it. This fading means the universe will lose the oldest light we can observe today. Without it, future civilizations will have no direct record of the early universe. The radiation that once filled all of space and told us about the universe's first 380,000 years will vanish from practical observation. This is another strange consequence of acceleration. As the universe grows, the very evidence of its origin becomes inaccessible. Even though the light still exists somewhere in the far reaches of space, it will be effectively undetectable. The story of the Big Bang, which we can study now, will be hidden from observers in the distant future. Future science may lack clues about the universe's origin because of how expansion affects observability. As galaxies move away faster and background radiation fades, many signals that tell us about the Big Bang will vanish. Observers in the far future might only see a few nearby stars and galaxies, giving them almost no information about cosmic history. They could know about local matter but have no way to measure the universe's expansion rate or detect its early light. Without supernovae or distant galaxies, critical tools for understanding the cosmos would be gone. This means future astronomers could struggle to reconstruct the story of the Big Bang. It is a strange idea that the universe itself hides its history over time, making it much harder to study as it grows older. What is easily observed now may become inaccessible in billions of years, leaving the universe appearing simpler than it really is. We live at a rare observational time in cosmic history. Right now, the universe is young enough that distant galaxies are still visible, and the cosmic background radiation is detectable. We exist at a moment when light from billions of years ago is still reaching us, providing a clear window into the past. This period is unusual because both the early light and distant objects can be studied together. In the far future, expansion will remove these opportunities. In the past, before stars and galaxies formed, there was also little to observe. This makes our current era unique. We can access both nearby and distant cosmic information, allowing science to understand the universe's structure and history. It is remarkable that humanity exists at this rare time, just when conditions are perfect to learn about everything from the Big Bang to galaxy formation. Now is unusually informative because both local and distant signals are available. We can study galaxies nearby, map their motion, and compare them to faraway supernovae and clusters. The cosmic microwave background still exists at measurable levels, providing a snapshot of the early universe. This combination of data allows scientists to calculate the universe's age, measure its expansion, and understand fundamental forces. Few other periods in time allow such detailed study. In the far future, distant galaxies and early light will vanish. In the distant past, complex structures did not exist yet. This makes our current era a sweet spot for cosmology. We have access to the ingredients needed to uncover the full story of the universe. The timing of our existence coincides with the availability of critical information that will not last forever. Timing affects scientific discovery because the information we can gather depends on what is observable. If humans had existed earlier, there would have been no galaxies or cosmic background light to study. If humans existed billions of years from now, most evidence of the early universe would have disappeared. Scientific progress is tied to what the universe reveals at a particular moment. Observers are limited by the cosmic environment. This shows that discovery is not only about intelligence or technology, but also about timing. The universe gives access to different clues at different periods, and our current moment happens to provide an unusually complete set of data. Without this timing, reconstructing the history of the cosmos would be almost impossible. In that sense, humanity's era is uniquely suited for understanding the universe in ways that might never be repeated. Gravity gathered the first clouds of gas after the universe cooled enough for atoms to form. Tiny fluctuations in density caused some regions to have more matter than others. Gravity pulled these denser areas together, concentrating gas into clumps. As the clumps grew, pressure and temperature increased in their cores. When the conditions became hot and dense enough, nuclear fusion ignited, creating the first stars. This process took millions of years, but it transformed simple hydrogen and helium into luminous objects. These early stars were the first sources of light in the universe, ending the cosmic dark ages. Without gravity concentrating matter, the universe would have remained a dark, diffuse expanse. Gravity acted like a sculptor, shaping gas into dense cores that eventually lit up as the very first stars. This shows that the large-scale structures we see today all started from tiny variations amplified by gravity over cosmic time. Early stars were extremely massive compared to most stars we see today. Some were hundreds of times heavier than the Sun. Their immense mass came from the abundance of hydrogen and helium in the early universe and the lack of heavy elements, which made star formation very efficient. Larger mass meant stronger gravity at the core, which increased temperature and pressure, causing fusion to occur much faster. These massive stars burned intensely, shining millions of times brighter than smaller stars. Their size and energy output made them very different from the Sun or stars in our neighborhood. The early universe produced these giants because the conditions favored rapid accumulation of gas. Studying them helps scientists understand how the first galaxies formed and how heavier elements first appeared. Their extreme mass shows how different the first stars were from the more familiar stars in the universe today. Because they were so massive, early stars burned out quickly. Fusion in the core consumed hydrogen at an enormous rate. Unlike smaller stars, which can shine for billions of years, these giants exhausted their fuel in just a few million years. Their intense heat and radiation blew away surrounding gas and triggered reactions in nearby regions. Despite their short lives, they had a huge impact on the universe. Their rapid burning also made them unstable, which led to spectacular deaths as supernovae. These explosions dispersed energy and matter across the universe. The short lifespan of massive stars means they acted like fireworks in cosmic history, brief but transformative. Their quick lives helped seed the universe with heavier elements far earlier than smaller stars could have. This rapid cycle of birth and death shaped the early chemical makeup of the cosmos. When these massive stars exploded as supernovae, they created heavy elements like carbon, oxygen, and iron. Fusion inside the stars produced elements up to iron, but the explosions generated even heavier elements through extreme pressure and neutron capture. These newly formed elements were ejected into space, enriching surrounding gas clouds. This material became the building blocks for new stars, planets, and eventually life. Without these early explosions, the universe would still contain only hydrogen and helium. Supernovae distributed heavy elements across vast distances, setting the stage for complex chemistry. Every atom of iron in your body, or oxygen in the air, originated in these first stars. This shows how the first massive stars not only lit up the universe, but also prepared it for the formation of planets and living things. Their deaths were not endings, they were the seeds of everything that came after. Iron did not exist at the time of the Big Bang. The universe began with only the simplest elements: hydrogen, helium, and tiny amounts of lithium. These were created in the first few minutes after the Big Bang through a process called primordial nucleosynthesis. Heavier elements, like iron, could not form in these early conditions because there was not enough density or pressure to fuse lighter elements into heavier ones. Iron and other elements required the extreme temperatures and pressures inside massive stars. Only after stars formed and went through fusion cycles did elements beyond helium appear. This means that everything heavier than helium, including the iron in planets and in your body, was created later. The Big Bang gave the universe the ingredients for stars, but not the full set of chemical building blocks. The production of iron was a later step in cosmic history, dependent on the life and death of massive stars. Gold and uranium formed much later than iron. While iron could form inside large stars, the heaviest elements require even more extreme events to be created. Gold, uranium, and other very heavy elements are mainly produced during supernova explosions or when neutron stars collide. These events create incredible pressures and neutron-rich environments that allow heavy nuclei to form. This means that the gold in jewelry or the uranium used for energy all originated in violent cosmic explosions billions of years after the Big Bang. These elements did not exist in the early universe, and even the first stars could not make them. The rarity of these events explains why heavy elements are less common than lighter ones. Observing heavy elements today tells scientists about ancient supernovae and neutron star collisions, helping us trace the violent history that produced the chemical diversity we see in the universe. Every heavy atom has a violent origin. Elements heavier than hydrogen and helium are not formed quietly or slowly. They require extreme pressure, temperature, and energy, found only in the cores of massive stars, during supernova explosions, or in neutron star collisions. Without these violent events, the building blocks for planets and life would not exist. Even elements like oxygen and carbon, essential for life, were formed inside stars before being scattered into space. Gold, uranium, and platinum required even more extreme conditions. This means that every atom heavier than helium has passed through dramatic cosmic processes. Looking at your own body, almost every atom originated in a star that lived and died millions or billions of years ago. This connects us directly to the violent processes of the cosmos. Life and planets exist because stars exploded, scattering their enriched material into the universe. The calm night sky hides a history of unimaginable cosmic violence. Galaxies recycle material over time. When stars die, they release elements into space, enriching surrounding gas clouds. This gas can later collapse under gravity to form new stars, planets, and even new generations of galaxies. Over billions of years, galaxies continue this cycle of creation and destruction. Supernovae, stellar winds, and collisions all contribute to spreading material. Older stars contribute heavier elements, while younger stars form from the enriched gas. This recycling allows galaxies to grow more complex chemically and structurally over time. Without this continuous recycling, galaxies would remain simple clouds of hydrogen and helium. The process also drives the formation of planets and life, because each generation of stars creates and distributes the elements necessary for chemistry and biology. Galaxies are not static. They are dynamic systems, constantly renewing themselves through cycles of stellar birth, death, and rebirth, making the universe an ever-changing laboratory of matter. The atoms in your body were reused many times before forming you. Every atom has a long history, passing through stars, planets, and clouds of gas over billions of years. Hydrogen in your water, carbon in your cells, and oxygen in your blood were once part of stars or ancient planets. When stars exploded as supernovae, they scattered these atoms across space, allowing them to join new clouds of gas that eventually formed new stars and planets. Over cosmic time, these atoms have been recycled countless times, moving from one object to another. You are made of matter that has been through countless cosmic events. This means your body connects directly to the history of the universe. Every part of you carries atoms that have witnessed the formation of galaxies, the explosions of massive stars, and the long expansion of space. In that sense, we are literally made of stardust that has traveled for billions of years. A strange fact is that most atoms in your body are older than Earth. The planet formed about 4.5 billion years ago, but the atoms that make up its material were created in stars long before that. Elements like carbon, oxygen, and iron existed in the gas clouds that later collapsed to form the solar system. These atoms were forged in the cores of massive stars, or in supernova explosions billions of years before the Sun and Earth appeared. This means that every piece of matter around you and within you has a history older than our planet. Even the gold in jewelry or the iron in your blood predates Earth itself. Thinking about it, this way highlights how connected we are to the universe. The material we take for granted has traveled across space and time, experiencing countless cosmic events long before it became part of our planet. Time behaves differently under extreme gravity because gravity affects how quickly clocks run. According to Einstein's theory of general relativity, the stronger the gravitational field, the slower time passes relative to a weaker field. Near a black hole or very dense star, time is stretched, and processes appear to slow down compared to distant observers. This means that events happening in extreme gravity take longer when measured from far away. Even light and signals are affected, as time and space are linked. This effect has been tested and confirmed on Earth with precise clocks at different heights, and it becomes extreme near massive objects. Understanding how gravity affects time helps scientists study the behavior of black holes, neutron stars, and the universe's earliest moments. It shows that time is not absolute. It is linked to space and gravity, meaning that the age of the universe can be experienced differently depending on where and how you measure it. Time in the early universe passed differently from what we experience today. The universe was extremely dense and hot, so gravity and energy were immense. This meant that time could be stretched or affected by these extreme conditions. Events that seemed fast to us now could have taken longer locally in the early universe, or vice versa, depending on conditions. Light and matter interacted constantly, and space itself expanded rapidly, influencing the passage of time. Observers measuring events in such extreme conditions would perceive durations differently from us today. This means our sense of a second or a year is very different from how time flowed in the first moments after the Big Bang. Understanding this helps scientists model early universe events, like inflation, particle interactions, and the formation of the first atoms and stars. Time is not uniform across the cosmos, and the early universe is a perfect example of how extreme conditions can change the rhythm of time itself. Time and space are linked because they are part of a single fabric called space-time. According to Einstein's theory of relativity, you cannot think of time separately from space. Events in the universe are measured in both space and time together. When space expands or curves due to gravity, it also affects how time flows. For example, near massive objects, time moves slower compared to regions with less gravity. Similarly, as the universe expands, the distances between objects increase, which affects how we perceive time over cosmic scales. This connection explains why measurements of the universe must account for both space and time simultaneously. Observations of light, motion, and cosmic events all depend on understanding this link. Without combining space and time, scientists cannot accurately calculate distances, velocities, or the age of the universe. This fundamental principle underlies everything from how galaxies move to how light travels across billions of years of expansion. Expansion stretches wavelengths of light because, as space itself grows, it increases the distance between the peaks of light waves traveling through it. Unlike objects moving through space, light does not need to be carried along by anything. Instead, the very fabric of space stretches, making the waves longer. Longer wavelengths correspond to lower energy and lower frequency. This means the color of light shifts toward the red end of the spectrum if the wavelength is in the visible range. Even light that started as high-energy ultraviolet or visible light will arrive at Earth as redder or infrared light, depending on how much space expanded during its journey. This stretching is measurable and provides key information about the universe's growth. It is not caused by motion through space, but by the expansion of space itself, which systematically changes the properties of light traveling across billions of years. Redshift occurs when the wavelength of light from distant objects increases as it travels through expanding space. This increase in wavelength shifts the light toward the red, or longer wavelength, part of the electromagnetic spectrum. Redshift is directly measurable by observing spectral lines in the light, which are produced by specific elements. Scientists compare the observed wavelengths with the wavelengths measured in laboratories on Earth. If the lines appear at longer wavelengths, the object is receding due to the expansion of the universe. Redshift is not caused by color change or heat. It is a direct physical effect of expansion. It is one of the most reliable ways to measure the motion of galaxies and other distant objects. By studying redshift across many galaxies, scientists can determine how fast the universe is expanding and track changes in expansion over billions of years. Redshift measures cosmic distance because the amount of wavelength stretching increases with how far light has traveled. Light from nearby galaxies shows small redshifts, while light from very distant galaxies shows large redshifts. By comparing the measured redshift with the rate of expansion, scientists can calculate how far the object is from Earth at the time the light was emitted. This method allows astronomers to map the universe and determine distances over billions of light years. Redshift also provides a timeline. The higher the redshift, the earlier in the universe's history we are observing. It is a fundamental tool for cosmology because it connects measurements of motion, distance, and time. Without redshift, scientists would have no way to quantify the expansion of space or understand the scale of the universe, making it one of the most essential observational techniques in modern astronomy. More distant objects in the universe appear older because light takes time to travel to us. Light moves at a fixed speed, so when we look at a galaxy billions of light years away, we are seeing the light that left it billions of years ago. This means we are observing the galaxy as it was long before the light reached Earth. The farther away an object is, the longer its light has traveled, and the earlier in cosmic history it is showing us. Observing distant galaxies is like looking back in time, letting scientists study the universe's past. This principle allows astronomers to understand the formation of stars, galaxies, and large-scale structures. It also means that, when we see the most distant light, we are seeing conditions that existed soon after the Big Bang. Distance and age are directly connected through the finite speed of light, providing a natural time machine across cosmic scales. Telescopes see into the past because they capture light that has traveled for millions or billions of years. When light leaves a distant star or galaxy, it begins a long journey through expanding space. The telescope collects this light when it finally arrives on Earth, allowing us to observe events that happened long ago. This means every image of a distant object shows it as it was, not as it is now. Telescopes with greater sensitivity and resolution can detect fainter, more distant light, letting us see earlier stages of cosmic history. Different types of telescopes detect different wavelengths, from visible to infrared or ultraviolet, revealing details invisible to the human eye. By observing light from various distances, astronomers can piece together a timeline of the universe's evolution. Telescopes act as time machines, showing the universe at different ages and allowing scientists to study how galaxies, stars, and planets formed over billions of years. The James Webb Space Telescope sees early galaxies because it detects infrared light, which is the stretched light from distant objects. As the universe expands, the light from ancient galaxies shifts to longer wavelengths, moving from visible to infrared. Webb's instruments are designed to capture this faint, stretched light with high precision. This allows it to detect galaxies that formed just a few 100 million years after the Big Bang. Older telescopes, limited to visible light, could not see these early structures because the light was redshifted beyond their range. James Webb's sensitivity lets scientists study the shape, brightness, and composition of these early galaxies. Observing them helps answer questions about how quickly galaxies formed and evolved. By capturing the first generations of stars and galaxies, Webb provides a window into a period of the universe that was previously hidden, allowing humanity to study the earliest cosmic structures in unprecedented detail. A strange fact is that early galaxies appear unexpectedly mature. Observations from James Webb have shown that some galaxies, formed less than 1 billion years after the Big Bang, already contain significant numbers of stars and heavy elements. They are larger and more developed than scientists predicted for such an early time. This challenges current models of galaxy formation, suggesting that star formation and cosmic evolution may have been faster than expected. These early galaxies also show organized structures, like disks and clusters, which were thought to take much longer to develop. The discovery is surprising because it implies the universe became complex very quickly after its formation. Understanding these galaxies helps scientists revise theories about the rate of cosmic evolution, star formation efficiency, and the early distribution of matter. The unexpected maturity of early galaxies highlights how much the universe still holds mysteries and how observations can challenge our assumptions about the past. The unexpected maturity of early galaxies challenges existing models because it shows that galaxies formed and evolved faster than scientists predicted. Traditional simulations of galaxy formation assumed that stars and structures would gradually build over billions of years. Finding large, organized galaxies less than 1 billion years after the Big Bang suggests that processes like star formation, gas accretion, and mergers happened more quickly. This contradicts some assumptions about how matter clumps and forms structures in the early universe. Models must now account for the speed at which early galaxies grew and became chemically enriched. These observations push scientists to reconsider factors such as dark matter distribution, the efficiency of star formation, and the role of cosmic feedback. In short, the universe appears more complex and organized earlier than models anticipated. This is a reminder that our understanding of the cosmos is still evolving, and new observations can overturn even well-established expectations about the early universe. Science adjusts theories by comparing predictions with observations and updating ideas when they do not match. When unexpected discoveries are made, like early galaxies appearing mature, scientists do not discard previous knowledge entirely. Instead, they revise models to incorporate the new evidence. This might involve changing assumptions, adding missing factors, or improving simulations. The process is ongoing. Every new telescope, instrument, or measurement can reveal information that requires adjustment. Scientists also test these revisions against other observations to ensure consistency. This method allows knowledge to improve over time, gradually producing a more accurate understanding of complex phenomena. In cosmology, where direct experiments are impossible, observations of light, galaxies, and cosmic background radiation guide theory. This cycle of prediction, observation, and revision is fundamental to science. It shows that understanding the universe is dynamic, flexible, and continually refined based on evidence. The Big Bang model is still incomplete because, while it explains many aspects of the universe, it cannot answer all questions. It describes the universe's expansion, the origin of the cosmic microwave background, and the formation of light elements like hydrogen and helium. However, it does not fully explain what caused the initial expansion, why dark energy exists, or why matter slightly outweighed antimatter. It also cannot completely describe how the earliest galaxies formed so quickly or the detailed behavior of dark matter. These gaps highlight that while the Big Bang model is powerful, it is not a final or complete theory of everything. Scientists continue to test, revise, and expand the model to account for new observations. Understanding the universe requires combining the Big Bang framework with studies of star formation, galaxy evolution, and fundamental physics. The model provides a foundation, but mysteries remain that challenge our knowledge. The Big Bang model explains many fundamental features of the universe. It accurately describes the universe's expansion, predicting that galaxies move away from each other in a way confirmed by redshift measurements. It also accounts for the cosmic microwave background radiation, which matches predictions about the temperature and uniformity of the early universe. Additionally, the model successfully explains the abundance of light elements such as hydrogen, helium, and lithium, produced in the first few minutes after the Big Bang. These observations are strong evidence that the model captures the broad structure and evolution of the cosmos. It also predicts large-scale patterns in matter distribution, helping us understand galaxy clustering and cosmic filaments. While it cannot explain everything, the Big Bang model provides a framework that matches a wide range of observations. Its success shows that despite unanswered questions, the model is a reliable starting point for understanding the history and growth of the universe. The Big Bang model does not explain everything about the universe. It describes how the universe expanded from a hot, dense state and how elements and galaxies formed, but it cannot explain the cause of the Big Bang itself. It also cannot fully describe dark energy, which is driving accelerated expansion, or dark matter, which makes up most of the universe's mass but is invisible and interacts only weakly with regular matter. Additionally, it cannot explain why the universe is so uniform on large scales, or why there is slightly more matter than antimatter. These gaps show that the Big Bang is not a complete theory, but a framework for understanding the universe's evolution. Scientists need additional physics to explain these mysteries, such as quantum gravity, string theory, or other ideas still being developed. Even though the model works well for observable phenomena, the origin and underlying mechanics of the universe remain partly unknown. Singularities, like the one predicted at the Big Bang, indicate missing physics because they involve infinite density and temperature, which current theories cannot describe. In a singularity, gravity becomes so strong that space and time break down, and the laws of physics as we know them stop making sense. This shows that our understanding is incomplete. Existing equations cannot handle the conditions at the very beginning of the universe. Singularities also appear in black holes, where matter collapses to a point of extreme density. Both cases suggest that a new theory, likely combining quantum mechanics and gravity, is needed to explain these extreme states. The presence of singularities is not just a mathematical problem. It signals that there is unknown physics waiting to be discovered. Studying them could reveal the true origin of the universe and the fundamental laws that govern reality under the most extreme conditions. The Big Bang was not the start of physics, even though it marks the beginning of the universe we can observe. Physical laws already existed, allowing space, time, matter, and energy to behave in predictable ways. The Big Bang represents the earliest moment we can study with current theories, but it does not create the rules themselves. Quantum mechanics, gravity, and other laws applied even during the first fractions of a second, though in extreme conditions we cannot fully simulate yet. The universe's behavior in those moments shows continuity with later times. Particles formed, forces interacted, and expansion began according to physical laws. This means physics is not born at the Big Bang. It merely describes what happens as the universe evolves from an extremely dense, hot state. Understanding this helps scientists explore earlier or more fundamental phases of the universe, without assuming a starting point for the laws themselves. Theories of earlier cosmic phases explore what might have happened before the Big Bang we can observe. Ideas include a period of cosmic inflation, where space expanded faster than light, and quantum fluctuations seeded the structure of the universe. Some theories suggest a cyclical universe, where contractions and expansions happen repeatedly. Others propose a multiverse, with many universes forming from quantum events. These phases might explain conditions that led to the Big Bang, such as why matter slightly outweighed antimatter, or why the universe is so uniform. While these ideas are speculative, they are based on physics principles and observations, like cosmic microwave background patterns. Studying these phases helps scientists go beyond the limits of the Big Bang model. They seek a deeper understanding of the universe's origins, before the first atoms or galaxies existed, trying to uncover what triggered everything we see today. Theories about what happened before the Big Bang remain largely untestable because we cannot directly observe or measure that time. Light and particles from those earliest moments cannot reach us, and any information about conditions before the observable universe is effectively hidden. Even the most advanced telescopes cannot detect signals from this era. Scientists rely on indirect clues, such as patterns in the cosmic microwave background or theoretical predictions from quantum physics, but these can only hint at possibilities. Without observable evidence, hypotheses about earlier phases remain speculative. This is why cosmology often distinguishes between what we can test and what we can imagine. While mathematics and theory can suggest scenarios like inflation or multiverse formation, confirming them experimentally is impossible with current technology. The universe keeps its earliest secrets locked away, leaving scientists to explore limits of knowledge and creativity, while accepting that some questions may remain unanswered. A strange fact is that the universe may have no true beginning. Some theories suggest that time itself could be cyclical, with periods of contraction followed by expansion, or that the universe existed in some form before what we call the Big Bang. In these scenarios, The Big Bang is not the absolute beginning, but a transition from an earlier state. Time, space, and energy might have existed in different forms, governed by physics that we cannot yet fully describe. This challenges the common idea that everything started at a single moment. If true, the universe could be eternal in some sense, without a defined starting point. While this sounds counterintuitive, it is supported by certain solutions in cosmology and quantum physics. Observing such states is difficult, but the possibility opens profound questions about the nature of reality, the origin of matter, and whether our observable universe is just one phase in an endless cosmic cycle. Causality may break down at Planck scales, which are the smallest measurable distances and times in the universe. At this scale, roughly 10⁻35 meters and 10⁻43 seconds, the effects of quantum gravity become extremely strong. Space and time fluctuate so violently that the normal order of cause and effect may no longer apply. Particles and energy can appear and disappear unpredictably, and the smooth flow of time we experience loses meaning. This is far beyond everyday physics, and even beyond the reach of current experiments. Understanding these scales is essential for a theory that unites quantum mechanics and general relativity. It may explain what happened during the very first moments of the universe. However, at Planck scales, conventional notions of before and after might not exist, meaning that our usual ideas about cause and effect could fail entirely, revealing a truly strange and unfamiliar realm of reality. There are strict limits of measurement in cosmology because the universe is vast, and some properties cannot be observed directly. Light from the most distant objects has traveled billions of years, and beyond a certain point, no information can reach us. The expansion of space stretches signals, making them weaker and harder to detect. Quantum mechanics also imposes fundamental limits. There is a smallest measurable distance in time, called the Planck scale, beyond which precision breaks down. Even with perfect instruments, these limits cannot be overcome. This means scientists can only study the universe within observable bounds, and some aspects may always remain uncertain. Despite these limits, clever techniques allow measurement of redshifts, cosmic background radiation, and galaxy distributions, giving insight into the universe's history and structure. Recognizing these limits reminds us that there are boundaries to knowledge, and some cosmic mysteries may be permanently hidden. Certainty decreases near the origin of the universe because conditions were extreme and physics, as we know it, breaks down. In the first fractions of a second, temperatures and densities were so high that our current laws cannot describe what happened. Quantum fluctuations dominated, space itself was rapidly expanding, and particles appeared and disappeared unpredictably. Observations cannot reach this time directly, and mathematical models encounter singularities where values become infinite. Because of this, scientists must rely on theories that extend beyond tested physics, like quantum gravity or string theory. While we can infer some properties from later light and matter distributions, the earliest moments remain uncertain. This uncertainty is not just a technical problem. It is a fundamental limitation in understanding the origin of everything. It shows that the beginning of the universe is a realm where science can make predictions, but absolute certainty about the first instant is impossible. After the violent beginnings, the universe transitioned into a period of calm expansion. During the first seconds, expansion and energy interactions were extreme, but as the universe grew and cooled, violent processes like inflation and rapid particle creation slowed down. Matter began to settle into stable structures, forming atoms, gas clouds, and eventually the first stars. Radiation no longer dominated completely, and light could travel freely after recombination, creating the cosmic microwave background. This calm expansion allowed gravity to start shaping larger structures, pulling gas into star clusters and galaxies. While early times were chaotic, the universe gradually became more orderly. The shift from violent, energy-dominated dynamics to smoother, predictable expansion created conditions suitable for galaxies, stars, and planets. Observing this calm expansion today, scientists can trace the universe's evolution and understand how initial chaos led to the stable cosmic web that exists now. Change in the universe slowed dramatically over time because, as expansion progressed, energy became diluted and processes like fusion and cosmic collisions happened less frequently. Early in the universe, events occurred rapidly. Particles formed, stars ignited, and galaxies assembled quickly. But over billions of years, as matter spread out and stars used up their fuel, the rate of major cosmic events decreased. Gravity still pulls matter together, forming galaxies and clusters, but large-scale violent changes like supernova-driven chaos or massive mergers became less common. This slower pace allows the universe to appear stable on large scales. Cooling also played a role. As temperatures dropped, particle interactions decreased, and chemical reactions in space became slower. While change continues at small scales, like star formation in galaxies, the overall cosmic rhythm has slowed compared to its energetic youth. The universe moved from chaos to relative stability, allowing structures to persist for billions of years. Large-scale structures in the universe are now stable because gravity has shaped matter into long-lasting forms like galaxy clusters, filaments, and cosmic voids. These structures have formed over billions of years as galaxies group together under mutual gravitational attraction. While individual stars or galaxies may change or collide, the overall framework, the cosmic web, is persistent. The patterns of galaxies and clusters we see today are unlikely to change dramatically in the near future. Even as expansion continues, these large-scale arrangements remain coherent because the forces shaping them operate over immense distances and timescales. This stability is what allows astronomers to study the universe's past. The distribution of galaxies preserves information about early cosmic conditions. In this sense, the universe has moved from a chaotic, high-energy beginning to a structured, enduring arrangement where the largest components provide a stable map of cosmic history. The universe today is relatively quiet compared to its early moments because the most violent events have mostly passed. In the first billion years, stars formed rapidly, supernovae exploded frequently, and galaxies collided regularly. Now, most regions of space are calm, with only occasional energetic events. Stars and galaxies are in stable orbits, and the majority of matter is spread evenly across the cosmos. Cosmic radiation has cooled, and the expansion of space is steady. This quietness allows galaxies, star systems, and planets to exist without constant disruption. Even though local events like star formation or supernovae still occur, they are rare on a universal scale. Observing this calm universe is very different from imagining its violent origins. Today, the cosmos is dominated by slow processes, long orbital periods, and stable gravitational systems. The quiet nature of the universe makes it possible for life to emerge and persist on planets like Earth. Extreme events in the universe are now rare because the energy density has decreased as the cosmos expanded. The most massive stars that fueled early supernovae have burned out, leaving behind stable, smaller stars. Collisions between galaxies still occur, but they happen over billions of years rather than continuously. Black hole mergers and neutron star collisions are infrequent compared to the constant violence of the early universe. The cosmic microwave background radiation has cooled to just a few degrees above absolute zero, so processes driven by intense heat and radiation are uncommon. While energetic events still shape parts of the universe, they are exceptions rather than the rule. Most matter now exists in stable galaxies, clusters, and intergalactic gas. This rarity of extreme events contributes to the calm, predictable universe we observe today, contrasting sharply with the chaotic, high-energy conditions of the first moments after the Big Bang. Stability increases as expansion continues because galaxies and clusters move apart, reducing the frequency of collisions and large-scale disturbances. Gravity still acts locally, holding stars in galaxies and galaxies in clusters, but on the largest scales, expansion dominates. This separation prevents violent interactions from being widespread. As space grows, regions of the universe become more isolated, allowing structures to evolve slowly and steadily. Star formation continues, but at a much slower pace than during the universe's youth. The expansion also stretches energy, cooling radiation and reducing extreme processes. Over billions of years, this leads to a cosmos where the majority of matter and energy exists in stable configurations. Even black holes and massive objects interact only occasionally. Overall, the universe moves from a chaotic early state toward long-term predictability. This increasing stability allows astronomers to study cosmic history, while life and structures persist without being disrupted by constant cosmic violence. The universe's origin was extreme, but its long-term behavior is slow, predictable, and calm. In the first moments after the Big Bang, conditions were unimaginably hot, dense, and energetic, with rapid expansion, particle creation, and violent processes dominating space. Over time, as the universe cooled and expanded, energy became less concentrated. Stars and galaxies formed, and gravity shaped matter into stable structures. Supernovae, galaxy collisions, and extreme events became less frequent, and the cosmic environment grew quieter. Expansion continues, but on the largest scales, it leads to gradual change rather than chaos. The cosmic microwave background cooled, galaxies settled into clusters, and the overall universe became organized. This long-term calm contrasts sharply with its fiery beginnings. The universe transformed from an unpredictable, high-energy state to a mature cosmos governed by slow, steady processes. Understanding this evolution highlights the contrast between the universe's violent birth and the peaceful, stable environment that dominates billions of years later, offering a window into cosmic history and its long-term future.